Welcome to Planet Earth for Educators, Properties of Matter. So this is material that we'll be covering in the first week of class. One of the primary properties of matter, so this is matter being the substance that we're looking at, is the state, what we call the state of that it's in. So this refers to the amount of energy present within the matter and the movement of the molecules. So in general, substances with a lot of energy and a lot of molecular movement will be in a gaseous or plasma form, and as the molecular movement slows down, they become more solid. So the phases are solid, liquid, gas. You might wish to include plasma as a state of matter that's more excitable than the gas state. This should be reviewed, but things that are in a solid state should not change their shape. They have a defined shape and defined volume. Things that are liquids will have a defined volume, but will be able to change their shape, so they will flow. So liquids and gases both flow. The difference being gases can also change their volume. So gases will expand to fill any space that you put them in, and you can compress them easily. Plasma is a lot like gases in that regard. In plasma, the excitement is so much within the molecules that the electrons start separating away from the nucleus of an atom. Plasma is actually the material that makes up the sun, a good portion of the sun, but we have plenty of examples of plasma right on Earth. If you have fluorescent lights in your classroom, that's plasma within in the lights when you run electricity through those gases. Neon signs have plasma within them. So you could include this as one of the states of matter that we talk about, although we won't be directly interacting with it. As I mentioned, the state that matter is in is going to be related to how much energy the molecules have. So usually this is related to temperature. So as things get colder, the molecules slow down and they solidify. And as you get warmer, the molecules start moving around more and you go from liquid to gas to plasma state. In general, as this happens, density will decrease as you increase temperature and go from a solid to a liquid as a gas phase. This is going to be true for nearly everything with the exception of water, which we'll talk about in just a minute. So in this image here, there's actually a photograph of a piece of dry ice, which is frozen carbon dioxide. And you can see that it is going from solid phase to gas phase. You can see the gas coming off of it. That is actually a process called sublimation, which is going directly from a solid phase to a gaseous phase. The corresponding name for going directly from a gaseous phase to a solid phase is deposition. And you can also see deposition in this image in those little crystals that have formed on the dry ice. Those little crystals are actually water ice. And the reason they formed there on the dry ice is water vapor that's in the air all around us has become extremely cold right next to the dry ice and gone directly from gas phase to solid phase and formed those crystals on top of the dry ice, the frozen carbon monoxide. Sublimation and deposition are probably the two phase changes or state changes that you might not remember. The others you probably have a pretty good handle on. Melting and freezing, going between solids and liquids, evaporation, going from liquid to gas phase, and condensation, going from gas to liquid phase. We're going to be talking about these a lot when we get to meteorology, but some of them will come up before then. As mentioned, the state that a particular substance is in, whether it's solid, liquid, or gas, is going to be related to temperature. This is probably a little overcomplicated plot, shows the various temperatures at which you would expect both dry ice and water to be in different states. So you can see that the dry ice, or the frozen carbon dioxide, is going to be solid at very cold temperatures up until you get to about minus 70 degrees Celsius, at which point it very rapidly becomes gaseous. You can have, or becomes a gas. You can have liquid carbon dioxide, but this only exists in this very small region of temperatures that is actually quite cold. So most of the time, if you take dry ice solid and bring it to room temperature, say in a classroom, it's going to directly go into gas phase, which makes it something really nice to work with in the classroom because you just get more carbon dioxide gas, which you've already got in the classroom, and it doesn't leave any trace behind. Water, on the other hand, if you use water ice, of course, and bring it into room temperature, it will melt. As you know, water freezes at 0 degrees Celsius, so At temperatures below that, you expect to find solid water or ice. At temperatures above 0 degrees Celsius, actually between 0 and 100 degrees, you have liquid water. And at temperatures above 100 degrees Celsius, you have water moving into steam, into gas. So this is critical for the way life has developed on the planet Earth, that we have liquid water under ambient temperatures. So between 0 and 100 degrees Celsius, you expect to find liquid water, which is part of all life as we know it. One interesting thing about water is that unlike other substances that we know about, as water gets colder, it does get denser like everything else, but at some point, at around 4 degrees Celsius, the density actually starts getting, instead of getting increasing, it actually starts decreasing, and the ice or the water starts becoming less dense. And then there's a discontinuity when the water transitions to solid phase and becomes ice, and it becomes significantly less dense than water. The result of this is that ice is less dense, or solid water is less dense than water, and will float. So in addition to looking at the phase of matter, we also look at some other basic properties, including mass. So mass is going to be the amount of matter that's present in an object. The weight for an object is going to be the force of gravity operating on that mass. So these are different quantities, although they're very related. And as long as you stay on the same planet, they don't change much. So the difference between mass and weight is mass is going to be multiplied by little g gravitational acceleration, 9.81 meters per second squared, which is gravitational acceleration on planet Earth, and that will give you weight. Units of mass are grams. Unit of weight, since weight is a force, are in newtons. We measure weight with a scale, which will actually measure the gravitational force. Say my weight is the gravitational attraction between me and the planet. Whereas we measure mass with a balance. So a balance is actually going to take gravity out of the equation by comparing the mass of an object with a known mass. So in the image here, you see a triple beam balance. So these might be like the balances that you see, say, in a doctor's office, where you put an object on one side on the little basket, and then you move the known weights over until they equal what you've put in the basket, and then you know what the mass of your object is. They do the same thing in the doctor's office. They just don't put you in as elaborate a basket. So this is a great, we use balances in order to determine masses. Another thing that we're very interested in terms of properties of matter, and this will be relevant in all of the topics we'll discuss in earth science, is the density of the material. Density, which is often signified by the Greek letter rho, is a measure of how much matter is in a given space, in a given volume. We calculate density as mass divided by volume. So for example, the units would be grams per cubic centimeter. So in order to calculate density, we first measure mass of an object with a balance, and then we measure the volume. We can measure volume of an object if it's a regular object by measuring it. So if I have a linear measure, if I have a rectangle or a cube of some sort, I can take a ruler and measure all the sides and determine the volume. If I have a perfect sphere, I can measure the diameter and calculate the volume using the equation for the volume of a sphere. If I have an irregular object, actually like either of the things in these images, the higher density steel chain or the lower density styrofoam pellets, I have to measure the volume in a different way. So either I estimate the volume by assuming a shape and I know it will be off, or I can measure the volume by using fluid displacement. In fluid displacement, we take an object and put it into a known quantity of fluid, like water, and then note the change in volume of the fluid. So in this example, we are measuring the volume of a rock, which is definitely something that we would do in this course. We put it into a beaker that has 600 milliliters of water in it. And when we add the rock into the beaker, the rock, of course, sinks to the bottom because it's more dense than the water. And we see the water level in the beaker rise up to 800 milliliters. So we didn't add any more water to the container. So that means that the change in volume has to be due to the addition of the rock. And the volume of the rock is 800 minus 600, or 200 milliliters. If we then take the mass of the rock on a balance, we can determine the density by dividing the mass by the volume. When we're looking at densities of different objects and deciding whether or not they're going to float or sink, what we're doing is comparing densities. In fluids, so fluids would be liquids and gases or things that are able to move around, which solids are not, the more dense object will sink and less dense objects will float. So in a glass of water, ice is less dense than liquid water, so it will float. It will not sink to the bottom, but it will float near the top of the water. In general, the density of water is about 1 gram per cubic centimeter at ambient temperatures, although it does change as the water gets hotter or colder. Ice is much less dense, about 0.9 grams per cubic centimeter. It's not a big difference, but this is enough to cause the ice to float to the top. If we were to put something like dry ice, which is solid carbon dioxide into the water, it will sink to the bottom of the glass because it has a density of 1.2 grams per cubic centimeter, which is much more dense than water. So one of the ways you can compare densities is to actually calculate it. You can determine the mass, you can determine the volume, and calculate a numerical density. Another way of determining density is by determining relative density, by putting objects into a fluid of some sort and seeing if they're able to float or sink. One of the things that we're interested in geology, and will be very important when we get to plate tectonics, is the density of different types of rocks. We use granite, which is what we call a felsic silicate rock, made mostly of silicon and oxygen, which are light elements, as a surrogate for the type of material that we'd find on continents. We use basalt, which is a mafic rock, also a silicate, but it also contains a large amount of iron and magnesium, which are heavier elements. So we expect basalt to have a higher density than granite does. Basalt is a surrogate for the type of material that we'd expect to find on the ocean floor. You might also look at rocks that have different properties, like pumice, which is a felsic silicate rock, like granite. You'd expect it to have a similar density, except that it has a number of vesicles in it, or little holes. So within these holes, you actually have air. So the overall volume of the rock actually contains quite a bit of air, which causes the rock itself to have an average density that's much less than that of other silicate rocks. So if you have two objects that have the same volume, but one has more mass, you'd expect the one that has more mass to be denser. If you have two objects that have the same mass, but one of them has a greater volume, you'd expect the one with the smaller volume to be denser. And you can test these out with activities to explore the effects, the relative effects of density, mass and volume on density. Something important to note, since this is an introduction to objects in science, is the first thing we're doing, is to pay attention to units. Units will help you understand if you're doing a calculation, whether you should be multiplying or dividing, and which things you should be using. Remember, length units are centimeters or meters. Volume is 3 dimensions. You're going to multiply 3 length units together. That will help you make sure that you've done the calculation correctly. So if you're actually calculating a volume, make sure you're multiplying 3 things together, or cubing something. Mass units that we use are grams, and density would be in grams per cubic centimeter. I should note that if you're doing fluid measures, we often use milliliters, which is a liquid measure. A milliliter is equivalent in the metric system to a cubic centimeter, which is very convenient for our purposes, for everyone's purposes. As a reminder, if you're measuring volume by liquid displacement, by fluid displacement, you must completely submerge your object, or you're not actually getting the volume of the whole object. So if your object's floating, you have to make sure you push it down beneath the surface of the fluid, or you won't actually measure the volume of the entire object. You'll just measure the volume that happens to be displacing fluid. And when you're measuring fluids within a beaker, you want to make sure that you measure from the meniscus, which is the center line of the fluid. The fluids are going to rise up a little on the edges of your beaker or your cylinder. So you want to get your eye right down to the meniscus level so that you can accurately measure the fluid displacement. So to sum up, density is directly proportional to mass. So as mass increases, density increases. Density is inversely proportional to volume. So as volume increases, density decreases. So if you have a handle on that and feel that you can explain it, that's what you need to know for the first part of the first unit of this class.